Hello, my name is Brentley, and my project is on atomic level degradation in heat exchanger pipes. As for the role of heat exchangers, uh, they transfer thermal energy between two fluids without mixing them. They enable efficient heating or cooling. They're critical for system performance, safety, and longevity. They're used in power plants, refrigeration, and HVAC, and cars. And there are four main degradation modes that happen. So for steam exposed steel pipes, there's oxidation, creep, corrosion fatigue, and grain boundary degradation. For oxidation, the high temperature steam reacts with the steel surface, forming oxide layers, things like ferric oxide, which can grow, crack, break, or spall off, weakening the pipe over time. And this is my model representing oxidation. Here are three grains with a visible grain boundary, and this is showing red oxygen atoms approaching it, and you can see some ferric oxide that has formed near the grain boundaries, and those green atoms are chromium. Creep damage results in voids and dislocation buildup. It's a gradual, continuous deformation that affects all metals and alloys under the combined action of temperature and stress. And its main driving force is a constant high temperature and mechanical stress over time. For corrosion fatigue, um, this is cyclic stresses from pressure or thermal changes, and it combines with steam or water corrosion, causing microcracks to initiate and grow faster than from fatigue or corrosion alone. And its main driving force is fluctuating stress with the pressure or temperature cycling, plus a corrosive environment like steam. For grain boundary degradation, um, this results from aggressive environments that cause elemental segregation, oxidation, or precipitation at grain boundaries, making them weaker and more prone to cracking or corrosion attack. And its main driving force is chemical segregation or oxidation. There are some new materials and fluids uh, that are being produced for the use in heat exchangers. And uh, of the alloys that have been made, there are these advanced austenitic stainless steels, ODS steels, which are oxide dispersion strengthened steels, and high entropy alloys, which are typically containing over 5 elements, and they offer a better resistance to oxidation and creep, but there are also some coolant innovations, like for example these molten salts. This company, Copenhagen Atomics, has these highly purified specialized salts that they use in heat exchangers, and the degradation rate is much lower when compared to steam. So they use them in power generation, and they can transfer the heat much more efficiently and operate at these higher temperatures with less pressure. And there is, of course, a reduced risk of steam-induced corrosion entirely. Now, for some closing thoughts, I think the atomic scale visualization helps us to understand what is happening, along with creating predictions and designing against failure. And innovations in both materials and coolants are key to heat exchanger longevity. Thank you.